If you are a farmer for years now, you've been familiar with problems brought by weather events such as flooding, tropical cyclones, and even the opposite extreme of it, drought. Especially in the Philippines, where all of these could happen in just 1 year. However, regardless of the years of experience, farmers are still at the mercy of these extreme events. We cannot control these things since they are governed by climate processes. What we can do instead is to figure out ways to respond to these challenges. To do that, we need to equip ourselves with the knowledge and tools to combat its impacts. For one, drought chooses no political or economic boundaries, meaning it affects all regions from local to even the global scale. From a farmer's perspective, months of rigorous preparation to grow the crops would go to waste under just one event. It could damage hundreds of hectares of farms and leave the farmer nothing to gain at all. Just in the recent El Nino episode in 2019, farmers in the municipality of Mamburao in Occidental Mindoro were affected by drought. Rivers dried out and failed to irrigate hectares of rice fields in the area. Hotter than normal temperatures and lack of rainfall brought by El Nino caused 35 to 100% crop yield loss in most farms. Back in 2019, farmer interviews were conducted by the Agricultural Office of Mamburao to document the impacts of drought and how it has affected the farmers. Here's drought from a farmer's perspective.
Nalulungkot sa pangyayari na ay kasapi ay nakadanas ng tuyot ng mga pananim sa matinding init ng araw. Sa katunayan po, itong eryang ito ay mahigit sa hektarya na walang nakuha kahit kaunti sanhi ng pagkatuyo ng pananim sa tindi ng init. At marami po sa amin ang bumaba ang ani sanhi ng matinding init ng panahon. So kami po ay humihingi ng tulong sa ahensya ng ating pamahalaan na ang aming irigasyon ay masuportahan, madagdagan ng mga kagamitang pampatubig.
So how did it come to this? Which factor delayed the onset of rain? How did the river run out of water for irrigation? And how do we respond to these threats in advance? This webinar will shed light on how end users and decision makers can take advantage of readily available data to understand drought and learn about the tools to mitigate its impacts. Specifically, we will tackle drought in the Philippine context and highlight the need of a national drought monitor system to enhance the nation's approach to reduce drought effects. And then demonstrate the importance of remote sensing in alleviating the challenges in monitoring farms, more specifically utilizing satellite data to monitor drought events in the country. And lastly, we will tackle the ways forward and how these technologies can be assimilated in the government operations and eventually translate to proactive advisories as we gear towards building a drought-resilient nation. Drought continues to threaten the food security of our country. Throughout the years, we have improved our ways in farming, as reflected in the increase in crop production, especially with rice and corn. Farmlands have increased in acreage, thanks to investment in research that resulted in more tolerant crops and technology that led to modern practices. However, as you can see here in this graph, this upward trend has been interrupted with episodes of drought, where severe events are often associated with El Nino. The Philippines' response to these climate-related impacts is through partnership with agencies such as Pag-asa and the Bureau of Soils and Water Management, or BSWM, under Department of Agriculture. Regional climate outlooks are released to the public for information on rainfall and warnings of potential El Nino or even La Nina. The El Nino Task Force was also created as a directive to enforce monitoring of the development of El Nino closely. However, we must know that water stress do not only happen during El Nino. Short-term events or dry spells also occur, which impacts crops and affect the overall yield. Drought has a complex nature, and one of the keys in dealing with it lies in our strength in monitoring. we need a proactive approach to improve our capacity for drought preparedness. That is also where research comes in. Project DCAF, or Drought and Crop Assessment and Forecasting Phase 2, is one of the initiatives funded by the government to advance drought research in the country. The project exists as an initiative to mitigate effects of drought in the Philippines using technologies like satellite imagery, GIS, climate models, and other geospatial tools. Through these tools, we get to understand the complex nature of drought. How does drought develop in the first place? The following explanation might give us an idea. Drought starts when there's a lack of rainfall in one place or region. If one area gets less of it for a certain period, this would manifest a meteorological drought. Let's follow where the water goes when it hits the ground. At the surface, the soil acts like a sponge that absorbs the downpour. When it gets too hot, water could evaporate into the air. This water shortage leads to crop damage. This is the case with agricultural drought. If the shortage goes on for months, water reservoirs could also dry up. This is now what you call hydrological drought. So, in simple terms, drought can be defined as a recurring climate phenomenon triggered by the lack of rainfall. So how do we monitor drought? Space technology has evolved through the years, and the advancement in agricultural monitoring shifted to remote sensing. Traditional approaches have always been the reliable way to monitor farms, but it was only relatively recent that satellite data has been adapted for regular observations. What is remote sensing? Remote means you are not in contact. You can sense your environment using drones, planes, and even satellites. The space race of other nations gave birth to applications on weather monitoring from space, which eventually triggered more innovations in satellites that can detect other features on Earth. This provided time and cost-effective options to monitor the Earth on a regular basis. Imagine these objects floating in space, controlled by the people on the ground as it takes images of the Earth as it orbits. Those that were launched 30 to 40 years ago could mean that they have 30 to 40 years worth of information about the Earth. This is also important to note because historical data provides patterns, and learning about patterns can help us predict what will happen in the future. This is where forecasting comes in. Additionally, as we utilize images of the Earth, we get to learn about its features, identify which are farms from afar, and even have an idea if the crops are in good condition. So, how does this work? Every day, fleets of satellites go around the planet to take images of the Earth using a light source, be it their built-in devices or the sun. Light reaches the Earth and bounces back towards the satellite sensors. By analyzing the retrieved signal, researchers are able to distinguish the various features on the Earth's surface. Just like how humans possess fingerprints unique to each individual, everything on Earth has a unique spectral fingerprint where you can distinguish one object with another by examining how much light at various wavelengths is absorbed or reflected. For example, healthy vegetation contains a lot of chlorophyll, thus reflects light at green wavelengths and at the near infrared, while absorbing light at the red and blue wavelengths. In contrast, unhealthy vegetation contains less chlorophyll, hence they reflect more red light and less at the near infrared. These are the spectral fingerprints of healthy and unhealthy vegetation. So what does this mean for the new normal? Collecting in-the-field information about crop conditions is difficult or even impossible when there's a pandemic and you can't travel. Satellite data fills in the gaps and lets the user monitor their farms safely from home. For this webinar, we will highlight how the tools of the project are utilized to monitor drought from space. Long historical records of a certain place or region is essential in defining what is normal. Climatologists do this by averaging 30 years of temperature and precipitation records. Understanding drought is similar to the way a doctor or nurse takes your temperature and makes other observations to understand if you're sick. Doctors have calculated that a person's normal body temperature is 37 degrees Celsius. How much above or below normal it is can indicate how sick you might be. Climatologists do the same thing to let people know if there's a drought and how severe the drought can be. Climatologists compare the information they collect on drought indicators to what is normal for an area to determine whether a drought is beginning or ending, or even how bad the drought might be. Remember how satellites could take images of the Earth and how this could provide us information about the health of the vegetation? Well, satellites could also measure the amount of rainfall and temperature on the ground. Temperature and amount of rainfall are the most noticeable drought indicators, but water levels in streams, rivers, and lakes, the amount of moisture in the soil, are also important drought indicators. In Project DCAF, we use rainfall and temperature as drought indicators to monitor drought. We also utilize drought indices that could be used to detect soil moisture stress on the ground. How do we derive indices? In deriving drought indices, we use parameters such as vegetation indices like Normalized Difference Vegetation Index and Land Surface Temperature or LST. These products have different spatial and temporal resolution. If you plot NDVI and LST parameters, it follows a triangular relationship, where high values of NDVI with low values of LST indicates maximum transpiration that can occur. This is associated with full covered vegetation areas, while low values of NDVI with high values of LST implies bare soil or heat stress vegetation. In general, the project utilizes satellite products to detect and assess, monitor, and forecast drought events. We use the Drought Index, SVTR, as it can estimate soil moisture stress on the ground. We also look at other drought indicators to monitor drought development, and lastly, we use models to predict for future drought events, so farmers can decide. Let's take a look at the science behind forecasting. There are two main types of forecasts, the first of which are statistical forecasts, which rely on historical records of input variables, or predictors, to forecast the target variables, or predictants. In this case, we use LST, NDVI, and Oceanic Nino Index as predictors to multiple statistical forecast models to generate forecasts of LST and NDVI, which we then use to compute SVTR. The second type of forecasts are the dynamical forecasts, which come from a global climate model, or GCM, that simulates the Earth's atmosphere. As dynamical forecasts typically have coarse spatial resolution of around 100 kilometers, the output of the GCM is used to run a regional climate model, or RCM. Using the underlying laws of physics and regional scale processes, finer resolution forecasts are generated for a specific region on Earth. For example, we have here 6-month forecasts at 100 km downscaled for the Philippines at 25 kilometers for the drought indicators, rainfall, LST, and soil moisture. So, the main difference between statistical forecasts and dynamical is that the former are made based on observed relationships of different predictors, while dynamical forecasts are made by running models based on the mathematical equations of atmospheric processes to make physically plausible predictions. To dig deeper on how we interpret and utilize these products, let's look at how we investigate drought events. Here, we focus on the recent El Nino during the 2018-2019 episode. In the earlier part of this webinar, we highlighted farmer interviews, which are actual reports from Mamburao, a region affected by drought during this period. What exactly happened in Mamburao? Why was Mamburao impacted, but not other neighboring municipalities? The coastal municipality of Mamburao Occidental Mindoro, at the southwestern coast of Luzon, has been classified as a climate type 1 according to modified Corona's classification of Pag-asa, which translates to an area with pronounced dry and wet seasons. The dry season starts during November and lasts until the end of April, while the wet season starts from June to September. Approximately 4,000 hectares of rice and corn areas are established in the municipality. 2 to 3 planting seasons are followed based on rainfall activity. During the dry season, irrigation is employed using surface and groundwater sources, such as the shallow tube well. In validation, especially in post-drought assessment, there are 2 basic things to accomplish. First, we need to identify which areas were detected by the satellite. And second, we need to confirm if the area is indeed affected by drought. Even if the drought event has ended, we could still investigate the past few months to see how drought developed in the region. This is where the importance of records and data comes in. How do we do this? Farm visits were conducted in May 2019 to collect rice and corn farm coordinates in Mamburao Occidental, Mindoro. This is important because we need to identify the farms as the satellite takes photos as it passes the region. Now, there were a total of 15 sites surveyed, with 12 damaged and 3 undamaged farms, each with corresponding farmer interviews. A standardized interview using the Key Informant Interview Questionnaire was used to collect farm and crop information. The established farm areas were then studied by utilizing historical satellite data to study past drought events. Crop damage reports were also collected from the municipal agricultural officers to verify the drought signals identified by the Standardized Vegetation Temperature Ratio Index. So looking at how drought developed in the region, we look at different parameters which were measured by the satellite. Different satellites passed the region and were able to record the amount of rain during this time period, as well as the temperature, vegetation health, and surface moisture estimation. At the start of planting season, the amount of rainfall is deemed normal but rapidly declines towards the growing season. Meanwhile, there is a positive temperature anomaly at the start of planting season, which returns to normal at the later months. Looking at drought indicators, NDVI anomaly and surface moisture is lower for damaged farms. Here, we use finer resolution NDVI from Sentinel-2 at 10 meters that was able to discriminate the damaged farms from the undamaged ones. Same thing with the surface moisture estimation derived from Sentinel-1 at 10-meter resolution. This vegetation stress captured by Sentinel-2 NDVI and Sentinel-1 surface moisture index corroborated with the crop damage, which ranged from 35% to 100% for the rice and corn crops in Mamburao. The affected stages of development were the vegetative and reproductive stages of the standing rice and corn crops in the area. Now, how about the index at the local scale? Here, we can see that SVTR peaked during the months of February to April. This was during the time when the crops present in farms were at the vegetative to reproductive stage, which could explain why some farms were partially to completely damaged. Actual photos of the rice farms that dried out during March can be seen here. Although SVTR was able to capture the peak of drought in Mamburao, it still failed to discriminate between the damaged and undamaged farms in the municipality. SVTR derivation relies on the long-term average of NDVI over LST ratio at 5.6 kilometers spatial resolution. Farm areas in Mamburao range from 2 to 10 hectares, which is smaller than the spatial resolution of SVTR, thus limiting the performance of the index. Current assessment puts SVTR at 50 to 78% accuracy. Hence, we look at other parameters at finer resolution so we could also investigate farms with more details. We also utilize soil moisture from AWS and look at the potential ways to calibrate satellite data to develop a soil moisture product. Now, aside from the drought assessment, we also looked at whether the forecast was able to predict drought in the region. We knew that stress can already be felt at the first quarter of 2019. However, you can see that drought was predicted to dissipate as the months progressed. Knowing this information is very essential to calibrate the models and adjust it so we can improve the performance of their forecasts. We need more truth, and we can get them from the farm and crop records of the farmers. This way, we get to figure out when to sound the alarm as we prepare ourselves for upcoming threats. These technologies are now accessible in the program website, the SARAi portal. Just go to sarai.ph and browse for the products of the project. Here, you can look at the forecast, which are aggregated for each municipality. Of course, these should still be used with caution, just like any other forecasts. So what's next for DCAF? How will its technology help the people in the long run?
One of the project's primary goals is to integrate the products into government agencies' operations. The DCAF project is a collaboration among IESM, the academic research arm of the project, and PAG-ASA and BSWM. These government agencies provide advisories and response to mitigate the country's drought impacts. I am Gayjane Perez and I am the project leader of DCAF. I specialize in remote sensing applications. In this project, we look at the potential of satellite data in strengthening the country's approach to understanding drought and building ways to help farmers avoid the negative impact of heat and water stress. While doing my postdoc at NASA, I have been exposed to how the US government approaches drought problems. They employ their own US Drought Monitor tool, developed after years of research, using satellite and ground data and different models to predict future stress. I believe that we can also do the same in the Philippines. As we heavily rely on agriculture, we must start maximizing the use of readily available data as satellite technology advances towards representing farms with more details. The way to do that is to enhance our product continuously. Product maturity undergoes several stages. For this to happen, we encourage the end users to take part by keeping records of their farm and working alongside agricultural technicians in collating this data. These datasets are crucial in validating and calibrating models for it to be more robust and dependable. As we take on the steps to build a drought-resilient nation, researchers must understand users' needs, not just fill the research gaps. As research answers questions, it may solve scientific problems, but it could also help realize the approaches to enhance farming practices, adopt proactive ways to be smart farmers, and then build on concrete measures to secure the food and water resources of the country.